Thank you all for being here on 9 a.m. on a Saturday morning. So before I start, the usual disclaimer for the Federal Reserve applies. So these are my views and not the views of the Federal Reserve System. So what I'm going to do in this paper is start with a fairly simple asset pricing model that's in principle can be used to price both equity and debt claims on a given firm. And usually the way these models work is that you have, in order to actually price the debt claim, you have to assume some sort of jump risk that the firm is exposed to. And in particular, if you're going to actually model what default is, default by definition is a jump risk because at the time of default, the value of debt is usually discounted and the value of equity jumps down to zero. Now, in the context of ambiguity aversion, if we think about what jumps actually are, jumps by definition are rare events, which means that we don't have a very good idea of what the distribution of either jump arrival times is or what the distribution is of loss in case of a jump. So what I'm going to do in this paper is actually think about an extension to kind of the standard ambiguity framework, which allows the agent to actually have different degrees of aversion to ambiguity about the Brownian motion shocks in the economy and ambiguity about the jump shocks in the economy. So just a brief summary of what I'm actually going to do in this paper. So I'm going to characterize equilibrium excess returns in the presence of these two sources of ambiguity. And in particular, I'm going to show that excess returns can be decomposed, expected excess returns can be decomposed into four components: a risk premium for the Brownian shocks, an ambiguity premium for the Brownian shocks, a risk premium for the jump shocks, and an ambiguity premium for the jump shocks. And then what's interesting in the version of the jump model that I write down, it actually turns out that the ambiguity premium for the Poisson shocks depends only on the degree of ambiguity about the distribution of the Poisson shocks, whereas the ambiguity premium for the Brownian motion shocks actually depends on the degree of aversion to both sources of ambiguity. Then I'm going to use some market data on financial institutions to actually get an estimate of what these two degrees of ambiguity aversion are, at least for these companies, with respect to these companies. And it turns out that in the data, it is actually true that agents exhibit a higher degree of ambiguity aversion towards Poisson shocks than towards Brownian shocks. And finally, as a bottom line, even in this very simple framework, allowing for these two sources of ambiguity aversion actually helps a lot in terms of matching both equity returns and survival probabilities, or CDS spreads. Okay, so in terms of a model overview, I'm going to start with a fairly standard intensity-based model of firm default. But I'm going to actually allow the default of a firm to actually have an impact on aggregate income with some probability. And I'm going to study the effects of different dimensions of ambiguity in this very simple setting. As you're going to see, some of the assumptions, for example, about what these Poisson shocks actually are very simple. Of course, we can write down more complicated jump distribution processes to match the data even better, but I wanted to start with a fairly simple model just to see how far we get. Okay, so we're going to be in an environment with capital N firms indexed by little I, and the default intensity of a given firm is going to be a linear function of the state variables. So, and in particular, the state variables are going to evolve according to a continuous time mean reverting process or an Ornstein-Uhlenbeck process, this dx. And so dw is going to be a vector of Brownian innovation, the standard Brownian innovations. Sigma x is the volatility matrix. Kappa 1 is the rate of mean reversion. And kappa 0, well, kappa 1 inverse kappa 0 is the level to which x mean reverts. In terms for pricing the equity claim, I'm also going to assume that there is an instantaneous log dividend stream, which is once again a linear function of the state variables. And finally, for the aggregate income process, again, the mean is going to be a linear function of the state variables. The income is going to load on the same vector of Brownian motions. And finally, with some probability pi I, if firm I defaults, there's going to be a consumption loss UIH.
Just to make sure, little x and big X are the same thing?
Yes. So, sorry, little x is the realization of the big X. Okay. In terms of preferences, so without ambiguity aversion, the representative household is very boring. So it's going to be a log consumption log utility optimizer. So in this case, we can write down what is the infinitesimal generator associated with all the shocks in the economy. And in particular, I'm going to separate this generator in two parts. A part that is responsible for the Brownian motions in the economy, and then a part that's responsible for the Poisson shocks. And so without ambiguity aversion, the value function is going to satisfy the standard recursion. So rho, which is the subjective discount factor, times the value function is just your instantaneous utility of consumption plus the infinitesimal generator applied to the value function. Now, I'm going to perturb the generators in two ways. So the generator responsible for the continuous shocks in the economy is just going to get these two terms added to it. So one which is kind of the distortion in the direction of the state variables. The other part is the distortion in the direction of aggregate income. And similarly for the jump part of the operator, once again, I'm just going to basically be distorting the jump distribution with an additive term. And associated with these distortions, as usual, we can compute the conditional relative entropy. So for the Brownian motion terms, it's just the usual squared norm of the distortion vector. For the jump term, it's slightly more complicated, but it's the same idea. Notice that here, in principle, you can actually have different distortions depending on which firm actually defaults. And we'll see how that plays out. Right, so given this perturbed operator, script g of little g and little h, we can write down the perturbed value function iteration. So again, we're going to kind of have the standard terms, which so we have a rho v, and then the instantaneous utility of consumption. But then tomorrow's realization of the value function is going to be discounted using the perturbed operator. And we're also going to penalize distortions using relative entropy. And in particular, when we have different coefficients on the two different contributions of entropy, this is what I'm going to be calling different degrees of aversion to misspecification of either the Brownian shocks or of the Poisson shocks. And so theta b inverse in particular is going to be measuring the degree of aversion to misspecification of the Brownian shocks, and theta j is going to be measuring the degree of aversion to misspecifications of the Levy density. Okay, so to go back, so we're starting with this jump operator, right? So you have your probability of the jump occurring. I mean, this pi I is basically conditional on a jump occurring. Does consumption actually fall? And then you kind of have the value function loss in case of a consumption fall, right? So on an intuitive level, you would expect agents to be more averse to ambiguity about things they know less about. So one way of doing that is to say that, in an economy where we have both continuous shocks that we observe continuously and these very infrequent shocks, you would expect to be more averse to ambiguity about the infrequent shocks. It does imply that you have two different entropy budgets, one for the continuous part and one for the jump part. Okay, so the way this aggregate income process is specified, while there's no default, you just have the drifted Brownian motion. If firm I defaults, so firm I defaults with probability lambda IT. If firm I defaults with a probability pi, you're going to have an impact on aggregate income. And in particular, with probability pi, you're going to drop consumption by UIH. Okay. Right, and then it should come as no surprise that the worst case likelihood distortions look very similar to what you would have in a standard setting. So the drift distortion is just theta B inverse times the appropriate first order derivatives of the value function. The distortion to the probability of default is an exponential tilt again to the value function, to the difference between the value function if the firm defaults and if the firm doesn't. You can also re-express the relative entropies in the standard way, but I'm actually going to be using the definitions of relative entropies. So bottom line is that I'm going to actually approximate the solution to the value function with a second degree polynomial in the state variables. And there should be a v of x and y. And it turns out that when you apply the second order approximation, with respect to y, you actually just get a first order term, and you're going to just have the usual discount factor. And then these coefficients for the expansion in terms of the other state variables are going to solve a very simple set of algebraic equations. Okay, so the only thing you need to understand from this slide is that nu1 is the linear loading on the states, and nu2 is the quadratic loading on the states in the value function. So in particular, we can now write down what the risk-neutral dynamics are going to be. So with respect to the state variables, you're going to start with the standard drift, or the historical drift, so kappa 0 minus kappa 1x. You're going to apply an ambiguity distortion, or an ambiguity shift to it, and then you're going to apply the standard risk price shift in this economy, which is just the covariation between the state variables and aggregate income. So given this functional form for the value function, gamma hat is actually a linear function of the state variables, which is why under the risk-neutral dynamics, you get a distortion to both the level of the drift of x as well as the mean reversion rate of x. And similarly for aggregate income, again, you start with a standard drift, you apply an ambiguity distortion, apply basically the price of continuous time income risk. And again, you can rewrite it as a perturbed level and a perturbed mean reversion minus the risk adjustment. Of course, with income, given that there are also these Poisson shocks, you're also going to be taken, when I switch signs, sorry. You're also going to be using the levied density under the risk and ambiguity neutral measure. So again, you're going to start with the historical probability of default, impact in case of default, probability of impact on income in case of default, and then this exponential term actually takes care of both the ambiguity adjustment as well as the adjustment due to the risk price of jumps. Okay, so if you look at this coefficient on UIH, you can rewrite it as 1 plus 1 over rho times theta g. So the 1 part is the risk adjustment, and 1 over rho times theta g is the ambiguity adjustment. So if you were to just have the risk premium in here, this would look very similar, except that this exponential would just be an exponential of minus UH. In terms of getting the asset prices, I'm going to use, to back up a little bit. It turns out that in this model, mostly because of terms like this, the pricing kernel is actually quadratic in the state variables. So I'm going to, and in particular, the pricing generator is going to have quadratic terms in the state variables. So I'm going to use a trick from fixed income to actually rewrite this quadratic term structure this quadratic dynamic pricing model as an affine pricing model. And the way it works is you basically augment the state space to model the quadratic factors. And one thing that this is going to do is actually transform this constant volatility model, but with squared factors, into a stochastic volatility model. And once we have it in this affine framework, then we can use standard results to actually price a lot of these claims, claims on these cash flows. Right. So basically, we're going to take quadratic terms of the form x prime, and we're going to transform that matrix into a vector. And in particular, so this is this vec operation. And moreover, we're basically going to drop the repeating entries. An equivalent way of doing it is to just take the lower triangle of that symmetric matrix and transform that into a vector. When we apply Ito's lemma, the drift of z is going to be a constant plus a loading on the original state vector and a loading on the segmented state vector. And then unlike x and y, we're actually the volatility of z is actually going to depend on x, which is what I mean by moving from a constant volatility model to a stochastic volatility model. And of course, these coefficients are related to the coefficients of the original process. I'm not going to specify what they are here, but they're very simple to actually derive. Okay, so given this augmented state space, we can do things like take the distorted default probability, write down a second order approximation again, and instead of having a quadratic term in x, we're just going to have a linear term in z. Similarly, for the risk-free rate, again, it's going to have this quadratic approximation due to the distorted default probability. And again, we can rewrite it as a linear function of both x and z. Right, so the infinitesimal generator looks very similar to what we would have in standard affine models. Okay, so now we can actually talk about asset prices. So in particular, if we think about pricing a claim at time capital T on with the cash flows that can actually, in principle, can depend on the realization of both x, y, and z. So I'm just going to define that as the price of G, and this price is going to be given as the solution to, to this partial integral differential equation, where we're going to take the pricing infinitesimal generator from previous slide and just compare it to the risk-free rate, where, of course, the terminal condition is that at the maturity of the claim, you're basically getting the cash flows. Now, what's nice about these affine models is that the prices of claims are actually exponentially affine. And in particular, if you consider a claim that is of the form an exponential of a linear function of x and z, then the price of that claim today is going to also be an exponential function of x and z, where these coefficients, alpha, beta 1, and beta 2, solve standard ordinary differential equations, and so this works if the discount rate is also, again, a linear function of x and z. Now, the other nice thing is, in these affine models, the excess return process, or the excess constant maturity return process, also is fairly simple. So you have an expected excess return part, of course. You have a loading on the vector of Brownian shocks, where the volatility now is, again, a stochastic volatility. And then you have this jump distortion as well. And then the expected excess returns are going to have 4 components. So we're going to start with the exposure to Brownian shocks. And we're going to apply 2 prices to it, a risk price and then an ambiguity price. And so to go back to your previous question, Martin, this is why I kind of needed to show what the new 2 and the new 1 parts are. And then the risk premium for default is given by this. I didn't write it out here, but in general, to decompose it into the risk part and the ambiguity part, you basically do the transformation from beta tilde to beta without tildes in 2 steps, once to just the risk neutral betas, and then from the risk neutral betas to the historical betas. So basically, if you think about what a risk-free zero coupon debt is, you're just going to be using the risk-free rate in the economy as the discount rate, and as I have shown, that can be approximated by an affine function. For the risky zero coupon debt, we're going to take the risk-free rate plus this distorted probability of default, and again, it's just going to be a linear function of this augmented state vector. Similarly, if we just think about the survival probability, so the probability of the firm surviving up to a given maturity, we're just going to take the risk neutral default rate, and again, that's just a linear function of the state variable. So for most of the assets, we're going to be in this affine world. Equity returns are a little bit harder because they're not a finite maturity claim. But again, applying a log linearization, we get back to a stochastic loading on the Brownian motion shocks and an excess return, where the expected excess return is going to have the same form. So in the 2 minutes that I have left, I'm going to say really quickly the empirical exercise that I'm doing. But basically, I'm going to be looking at 13 of the largest financial institutions. And I'm going to be looking at CDS spreads, or more specifically, I'm going to transform the term structure of CDS spreads into a term structure of survival probabilities to stay in this linear framework, well, almost linear framework. And then I'm also going to be matching that data to equity excess return data on these companies. Right, so this is what equity returns look like, CDS spreads, and the implied survival probabilities. But the nice thing is that in this affine framework, if we actually stack all the observations, at all dates and for all companies, then we get a fairly simple system of the state vector evolutions and of the market variables evolution, so either the excess returns or the survival probabilities. Which basically, and this Vy, Vz, and just little v are measurement errors. So the way the empirical strategy is going to work, I'm going to identify what the factors are, I'm just going to take the principal components from equities and survival probabilities. To kind of tie my hands a little bit, I'm going to assume that the levy process driving defaults and impact of defaults is just going to be the same across firms. In principle, if you also add kind of historical default probabilities in here, you can relax this assumption a little bit. And to match the parameters of the process, I'm basically going to match some moments from papers that have looked at this rare disasters literature. And and given those parameters, I'm actually going to use a regression-based approach to estimate the parameters of the continuous parts. Right, so we're going to start by basically estimating the evolution of X. It's very simple, standard VAR approach. Using the estimates of X, you can actually estimate what epsilon is. And given your estimate of epsilon, you can actually use a seemingly unrelated regressions approach to estimate the coefficients in, for example, the aggregate income evolution, but also in the evolution of excess returns. Now, this lambda matrix, which is the loadings of excess returns on all the state variables, we actually have an alternative form for it, which depends on the ambiguity parameters and parameters of the value function. But given the value function recursion, we actually know what these value function parameters are in terms of the parameters of the underlying process and in terms of these, in terms of theta b and theta j. So to actually estimate what these are, I'm just going to use a minimum distance estimator between the lambda that we get from this regression-based approach and the lambda that we should basically have given the theory. And I'm out of time, so.
Can I ask you what's on the next slide that summarizes the results?
So parameters, well, basically theta b is bigger, theta j is bigger than theta b. And so you can look at things like jump probabilities, for example, or relative entropy contributions, and variance explained, and things like that.